Welcome all to this new reading group session organized by ContinualAI. Today we have the pleasure to host Benjamin, Ehret, then Christian, Henning, and Maria Cervera that are going to talk about their recent work, continual learning in recurrent neural networks. So thank you guys for joining us today. I'm sorry if you don't see me, maybe because my webcam, I don't know, is not working at the moment, but welcome and please go ahead with your presentation.
Okay, thanks a lot, Vincenzo, for the introduction. And yeah, of course, thanks a lot for inviting us today to talk about our work. So as you said, it's some work that we posted a few months ago in Archive and where we looked at continual learning in recurrent neural networks. So as you all know, there's been a lot of recent interest in continual learning methods that overcome catastrophic forgetting, but most of the studies that have been done were done in static data. So for example, for image classification problems, but it has remained unclear how all of these methods that have been developed are when applied to recurrent neural networks for dealing with sequential data. So this is what we look at in this study, and in particular, we try to contribute to the development of continual learning methods for recurrent neural networks in 3 ways, and each of these 3 ways which will give the structure of the talk today. So we will have 3 parts, and each of them will be presented by one of the main authors of the paper. So I will start by talking about how we identified the elements that critically affect weight-important methods in RNNs. Then Christian will talk about an approach based on hypernetworks that has the potential to overcome some of the limitations of weight-importance methods in this setting. And for this, you will deviate a bit and talk about a previous paper that was also published by our group. And finally, in the last part, Benjamin will present what we think is the first systematic comparisons of established methods for continual learning in RNNs. So because the talk is going to be a bit longer, all three of us are talking. We will kindly ask you to keep most questions for the end and the discussion for the end. But of course, if there is an issue with understanding that you need to solve, please go ahead and interrupt us.
Sure.
So with that, let's start with the first part. So the analysis of weight importance methods in RNNs. And let me start by clarifying what we mean with continual learning. So we consider a setting where we have a discrete set of tasks D1 to DT, where the data set consists of a collection of input and output samples, and each data set has a particular joint distribution. Now the question arises of how to learn those tasks sequentially, so without obtaining ID samples from the overall joint distribution. And so this is illustrated by the little animation here on the left, where we see that the red dot is giving samples first from the polynomial on the left that corresponds to the first task, and then from the polynomial on the right, which corresponds to the second task. So as you know, when faced with this scenario, neural networks typically suffer from catastrophic forgetting. And for this, a variety of continual learning methods have been developed over the years that include dynamic architecture approaches, complementary memory systems, and regularization approaches. So regularization methods are very interesting. They work by imposing constraints on certain weight updates. And they are very versatile because they don't require an increase in the capacity of the network as dynamic architectures do, but they also don't rely on the rehearse of past data, as is typically the case on complementary memory systems. And this makes them very applicable to a wide variety of scenarios. And although so many different methods have been developed, as I mentioned before, it has remained unclear whether this can be used off the shelf for continual learning in RNNs. And this is the question that we tackle here, and we will tackle it by focusing on a particular family of methods within regularization methods that are weight importance methods. So weight importance methods work in a very intuitive way. They calculate how critical or how important any given weight is for solving previous tasks, and then they make these weights more rigid when learning subsequent tasks. And classic examples are elastic weight consolidation or synaptic intelligence. So to give you a visual intuition of how these work, consider the case of a neural network with only two weights that define the two axes, and where EWC first learns a first task where a low error is indicated by this area. And in the first task, it's able to find an optimal solution. And then when facing a second task, it has to find a trade-off between solving the second task well enough, but also maintaining a good performance on the previous task. So it will have a solution space that is a compromise between the two. And this is achieved by introducing a regularization term in the loss function that makes sure that every individual weights that are given by the psi's here stay close to their values before learning the current task, with a strength that is proportional to this value here, that is called the importance of the weight. So this value here, this variable is going to be very important for the rest of the analysis. So as I said, it just indicates how strong the regularization will be for each of the weights. Now it becomes clear that these methods are affected by the stability plasticity dilemma, which refers to the fact that the networks have to remain stable in order to maintain previously acquired knowledge, but they also need to be plastic in order to be able to learn upcoming information. Okay, so now the question that we ask is whether recurrent neural networks are differently affected by the problem of catastrophic forgetting as feedforward networks. And actually, recurrent neural networks differ from feedforward nets in several ways that could be important for this type of methods. The first one is that there is a sequential reuse of the hidden to hidden weights, as is depicted in this little schematic here. So because of this reuse, it means that there will be further constraints on the hidden to hidden weights. And therefore, we imagine that this could have some type of influence in the computation of the importance values. Then the second thing is that these networks require some type of working memory to solve the task, because there is this temporal component. And working memory is typically defined as the ability to store and manipulate information from individual samples. Now, because all of the information from any given sample has to be contained in the hidden state here, one can see working memory a bit as the amount of information that is maintained in the hidden space, and thus one can think of quantifying it as the dimensionality of the hidden space. Now that we have these two factors that could potentially affect weight importance methods, over the next few slides, we're going to try to identify which or whether any of these two factors do actually influence the methods. So for this, we start considering a very simple case where we have a vanilla RNN that is linear. So the hidden state update is given by this equation, where to compute the hidden activations at every time step, we only have to multiply the previous time step by the set of hidden to hidden weights. So as you see, there's no nonlinearity applied anymore. And we also assume that all the input has already been presented to the network, so that xt doesn't come into the equation now anymore. We also assume that all the tasks are completely different and they cannot share computation, and that they all are solved simultaneously within the hidden state. And this can be commonly the case for methods such as EWC that are not task conditioned, if the task identity cannot be inferred from seeing the input data. So it can be shown that to prevent interferences in this very specific scenario, task-related information has to be kept in orthogonal and task-specific subspaces. So to get a bit of a visual intuition of what is going on here, we can depict the equation above with this little schematic, where we consider three tasks, each giving a different color. And we see that the information of all the subspaces is completely entangled, both in the hidden space and in the manipulations that are happening in the hidden to hidden weights. Now, one can apply a certain change of basis to disentangle these subspaces. And one particular way of this new transform weight matrix that could allow for these subspaces to be orthogonal is this block diagonal matrix that we can see here. And now we see that by applying this transform weight matrix, all information from the green subspace that was in HT will be transformed into will remain within the same subspace, basically. Now, what we see here in the lower right corner is so to say, our free capacity to learn new things. And it's easy to see that if we increase the size of the blocks, that capacity reduces. And this increase in the blocks happens when the hidden dimensionality for each task is bigger. So according to what we said before, if the working memory per task is bigger. Now, what happens if we want to learn another task is that we have very little capacity remaining, and so probably we won't be able, the network won't be able to perform really well on this last task. So because weight importance methods work by constraining these hidden to hidden weights in order to maintain this orthogonality of the subspaces, we can expect that the number of weights that are important increases with not only the working memory requirements per task, so the size of these blocks, but also the number of tasks, so the number of blocks. Okay, so after getting this intuition in the simple case of linear RNNs, we go on to nonlinear RNNs, where we further want to make sure whether it's the working memory requirements or the sequence length that have an effect. And for this, we use a synthetic data set that allows us to disentangle these two factors. So we consider a simple task that's using the literature that's called the copy task, which in principle is quite simple. You have a binary random input that is presented to the network, a certain signal to the network that's called the stop bit that I'm showing here. The network knows that it has to start reproducing the input that it received. Now, we chose this task because it's really easy to manipulate in the case the working memory. So just by increasing the length of these patterns, the network will have to remember a lot more. So this is what is shown here. Just we increase it, and then logically, we're increasing not only working memory, but also weight reuse just because we have so many more time steps. Now, if we wanted to control for this, so just for example, increase the number of times that we reuse the weights without increasing the working memory, we could give an input that's slightly different, where the pattern length remains the same, but where we simply increase the delay between input presentation and output reconstruction. So with this task, what we did is to train networks individually. So this is important to keep in mind here. We really don't have a continual learning scenario here. It's really to get an intuition of what is going on. And we started with the case where we increase both weight reuse and working memory by making these patterns longer. And we first wanted to verify whether this intuition that we had that working memory corresponds to hidden dimensionality holds. And so this is what I'm showing you here. The x-axis shows time, where the 0 corresponds to the stop bit presentation. So it really separates the time steps during which the input was presented on the left, and the time steps during which the output has to be reconstructed. And the different colors show different lengths of the pattern. And what we see is that very nicely, there is a very nice relationship that the longer these sequences are, so the higher the working memory, the higher the intrinsic dimensionality of the hidden space. So after having verified this, of course, what we're actually interested in is in seeing the effect that this has on the weight importance values. And this is what I show you here. We have in the axis the input length. So this corresponds to the different shades of red here. And what we see is that the mean importance values increase with increasing pattern lengths. Now, of course, remember that here we're not only increasing working memory, but also weight reuse. So for that, we repeated the same experiments, but keeping the pattern length the same and increasing this delay before output reproduction. And this is what we're doing, what we're showing in this second row. And as expected, we see that the dimensionality of the hidden space is identical in all cases. So working memory corresponds to the dimensionality. But importantly, we also see that the mean importance values don't increase in this case. So we believe this nicely shows, I believe this nicely shows that it's the higher working memory requirements and not necessarily the weight reuse that lead to an increase in weight importance values. Okay, so with this, let me conclude the first part. We argue that continual learning in RNNs remains an understudied topic, and we think it's a topic worth studying because RNNs have certain particularities that could mean that they are differently affected by catastrophic forgetting. And here we try to investigate the effect of these particularities by studying how weight importance methods perform on them. And we studied this by looking theoretically at linear RNNs and empirically at nonlinear RNNs. And then we concluded that it's the increased working memory requirements and not necessarily the sequence length that can lead to an increase in weight importance values. Now, an open question remains, and it is whether there is any continual learning approach where this stability plasticity dilemma is not directly affected by the recurrent nature of the task, as with the case of weight importance methods. And this is what Christian is going to talk to you about now.
Okay, so in order to pick up on Maria's question, I first take a step back and want to introduce you a method for continual learning based on hypernetworks. And as you will see by the end, this method is essentially agnostic to the fact that the main network does a recurrent processing of the data. This method has also been published by our group, and it is joint work with Johannes van Oswald and Joao Sacramento. So let's first start by introducing, let me introduce to you what a hypernetwork is. So a hypernetwork is essentially just another neural network with parameters theta that receives input embeddings E, and the output are the parameters psi of a main processing network. The name hypernetwork has been introduced a couple of years back by David Ha, but the idea that an auxiliary neural network is used to generate weights of a main processing network is already much older. And there are many applications of hypernetworks. An example is weight processing, as I will show to you in weight compression, as I will show to you in the next slide. And there's uncertainty modeling, which is very interesting because you can use hypernetworks to model implicit distribution in the case of Bayesian neural networks, and many more. And we, of course, focus on continual learning here today. So when you're first exposed to the idea of hypernetworks, you might one might think it's a naive idea because the output of such a hypernetwork must be huge to produce all the weights of another neural network. But in fact, these networks are usually used in a compressive regime, and importantly, all the results that we will present to you today are obtained such that the number of trainable weights in a hypernetwork is actually less than the number of trainable weights in the main network only, which is used by all the other methods. And a very way to achieve such compression is using a chunked hypernetwork, where you simply chunk the weights of the main network. And here for illustration, I just use a layer-wise chunking. And then you have a very small hypernetwork with parameters theta that receives an input embedding, a chunk embedding, to produce first the first set of parameters. And then if it receives another low-dimensional embedding, produces the next chunk of parameters, and so on. And overall, you can use that scheme where with low-dimensional chunk embeddings and the small hypernetwork with parameters theta to essentially have much less parameters than the main network parameters psi would have. Now, this scheme allows you to produce a single set of main network parameters psi with the hypernetwork. Now, the power of hypernetworks comes, of course, into play because you can produce conditional weights. For example, you might have a condition T encoded by this embedding ET down here in order to get for each condition a separate set of main network weights. So why would one use hypernetworks for continual learning? So in continual learning, we're trying to learn a set of tasks, and here depicted by these 3 different polynomials we want to learn sequentially. And as you can already imagine, learning a single network to fit all 3 polynomials might be pretty tough. So it might seem ideal that we learn a separate model for each of them. So a continual learning method like progressive neural networks might seem a good fit here. But unfortunately, these methods have linear increase in resources, which is not very desirable. Now, hypernetworks give you the possibility to learn task-specific models and compress them all into one shared meta model. And I quickly want to depict it to you in this little schematic over here. So we have so hypernetwork is just a function from an embedding space to the weight space of your main network. And here I plot such a function at initialization. And now when you learn the first task, the goal is that for the first task embedding E1, you're trying to find a viable solution for this first polynomial. Now, when you go on and want to learn the second task, you can freely change this hypernet function. The only thing you need to ensure is that this first solution, so the output for the first task embedding, remains fixed. And then going on to the next task, the same is the case. You can freely change this hypernetwork function. Just need to make sure that these already found solutions remain fixed. Of course, in practice, you can also learn these embeddings down here, which I just kept fixed for illustration. Now this input-output mapping regularization, or keeping input-output mapping, that's a common theme in continual learning. For example, replay usually is employed in the exact same way. You replay all data in order to make sure that the functional mapping doesn't change for this old data. The difference is, for complex data sets, you usually replay thousands of data sets to represent the input distribution of previous tasks. Here you only need to represent, or here you only need to fix one input-output mapping per previous task, which you will see in a second, is extremely beneficial for continual learning. Now, how do we achieve this input-output mapping fixing? So we just use a simple L2 regularization of the hypernetwork outputs. So down here, you see the complete loss function. And this first term is just the loss for the current task where we have the data set available. And then the second term over here is a sum over all previous tasks. And what you want to achieve is that the hypernet output for any of the previous task embeddings remains constant or remains the same as the hypernetwork output has been before you started learning the current task. Now, this is just the most simplistic way of how to realize such a regularization. You can, of course, think of many enrichments. For instance, to overcome the effect of the linear increase with the number of tasks, you can just randomly subsample at each mini batch a separate set of previous tasks, which we showed works well as well. You can also work on the uniform regularization here and use a weighted regularization using any weight importance scheme or pruning scheme to figure out which hypernetwork outputs are more important. So one question that remains is, now, do I always need to provide the task embedding to the system in order to do inference? So in certain continual learning scenarios, it might be required, or it actually might be required that the system automatically infers which task it has to solve, so that from the input alone, if that's possible, it figures out which task it is solving. In our paper, we provide 3 different approaches to do that, and I want to briefly sketch 2 of these. The first one is based on predictive uncertainty. So for each task embedding, we look at the corresponding prediction the main network does, and we assume we can compute some kind of uncertainty estimate from this prediction. Then we can use this uncertainty estimate to do out-of-distribution detection and choose the task which corresponds to the lowest predictive uncertainty. Now, another interesting approach is to use generative replay. So what you see over here is a replay decoder, which is essentially just a generative model, and this is also typically used in continual learning. Now, the problem is that in this way, the problem of continual learning is shifted to the replay model, and the way that it's usually dealt with is that you train the replay model on its own replayed data in order to prevent catastrophic forgetting. Now, since we never have perfect generative models, this introduces a distributional shift and errors will accumulate over time. So your generative distribution of previous tasks will become worse and worse. Now, the hypernetwork allows us to learn a task-specific generative model, and then the continual learning is just transferred to the hypernetwork output regularization, and we never have to train the replay model on its own replayed data. Then once I have that, I can replay data for all previous tasks and use the current task data to essentially train a classifier in a pseudo multitask session where I have all the data available. And then during inference, I only need this classifier and no hypernetwork is necessary anymore. So let me quickly show to you how this approach works in practice. So here I'm concentrating on a permuted MNIST benchmark. And first we look at the simple scenario where the task identity is given to the system. And if you look only at 10 tasks, all the benchmarks I list down here perform reasonably well in this scenario. If you move to 100 tasks, you also already see clear differences. So what you see here is after having trained on 100 tasks, you go back on each individual task and ask which is the QC it still has in performing the task. And as you see, very interesting for DGR, which is a generative replay model, you catastrophically forgot all the early tasks that you've seen during training, which essentially accounts to what I just explained to you, that you have this distributional shift because you train on the data, on your own replayed data. If you move on to a more complex continual learning scenario, where you have to infer the task identity from the input, then already for 10 tasks, the methods synaptic intelligence and online EWC already fail in the way they're typically ported to the CL scenario. And the replay method DGI usually still works relatively well, but if you now move to 100 tasks, it also catastrophically fails, while the hypernetwork, as you see, has essentially no problem with it, because for the hypernetwork, it's still a simple task to solve. It just has to fix 100 input-output mappings for the previous tasks. So to summarize what I just explained to you, so hypernetworks are a way to compress task-specific models in a single shared meta model, and we can prevent catastrophic forgetting, in this case with a simple output regularization. And what we also show in the paper is that we can achieve forward transfer through the use of this shared meta model. And you also have seen that this method readily applies to generative models. Now, to connect back to what Maria told you, we look again at the schematic. When you use weight importance methods such as EWC, you first try, of course, to find a good solution for the first task. And now you need to find a trade-off, an overlap between these two tasks. And this trade-off might not be desirable, or it might not even exist. Now, the hypernetwork allows you to sidestep this problem, and you can learn task-specific models. So this is one benefit. The other benefit, and now connecting to the overall theme of this talk, is even for recurrent neural networks process the data sequentially, they still have a single static set of weights. And so if you translate the problem of continual learning to the hypernetwork still has to produce a static output for an RNN, which can be regularized in the same way as for feedforward networks. So it's a very interesting question to ask whether hypernetworks or how a hypernetworks approach performs when you do CL with recurrent neural networks. And this is now what Benjamin will explain to you.
So Maria and Christian talked about the theoretical limitations and advantages of weight importance methods and hypernetworks respectively, but the question is of course whether these theoretical differences actually manifest themselves in experiments on real-world data. So we set out to compare these methods alongside some other continual learning approaches in different real-world data sets, and we hope that this will also be a resource for the community in the future to compare to when people develop new methods. So we performed continual learning experiments on 3 different data sets, and I'm going to walk you through the results, and on the way I'll explain the experimental details as well as the methods that we use. The first data set that we consider is AudioSet, which is a collection of annotated 10-second audio snippets that are organized into different classes, shown here on the left. And this data set has been previously used for continual learning. So we used these previously used quality criteria to filter the classes. Then we selected 100 out of these classes according to the number of samples and subdivided them into 10 groups of 10 classes, such that we had 10 different classification tasks for continual learning. Before I go into the results of the different experiments that we did, I quickly want to sketch the experimental procedure that we used. So we performed extensive hyperparameter searches for all of the methods, where we really tried to give the same resources to all methods in order to get a fair comparison. And additionally, we also, as Christian already mentioned, made sure that all of the methods have the same number of trainable parameters in order to stay fair. We quantify our results looking at during and final accuracies, where during accuracies refer to the accuracy on a task when tested directly after training, so there can't be any forgetting. And final accuracies refer to the accuracy on tasks when tested after training on all of the tasks. So now looking at the methods, we here the first three methods are continual learning baselines, where multitask would have the unfair advantage that it has always data available from all tasks, which is not the case usually in continual learning. The from scratch baseline has also an unfair advantage in that it has a different model per task. So here we have the exception that this baseline really has much more capacity than the other ones, and these two really serve as kind of upper bounds for what the continual learning methods can achieve. Then the fine-tuning baseline is here we train a model sequentially on all tasks without any protection against forgetting. So this is to display how much forgetting there is. Then hypernetworks and online EWC we talked about already before. Synaptic intelligence is an additional weight importance methods that we also use for comparison. Then we also consider an approach called masking here, which is also known as context-dependent gating, where per task you have a binary mask, which defines a subnetwork that is used only in this task, or that is used in a specific task. But if you look at many tasks, then there can, since these subnetworks are randomly chosen, there can be overlaps between the subnetworks. Such that there can again be some interference. That's why you can also use synaptic intelligence on top of that to protect against this interference. And then finally, we also consider coarse sets, which is a bit of a different approach, where you save samples from old data sets or from previous tasks. And here the number refers to the amount of samples that are saved. This task is this method is a bit different conceptually because it might not always be possible to store these samples from old data sets, for example, because of privacy reasons or just because there's no capacity or memory capacity for storing. But we also want to point out that this approach can be integrated with all the methods, all the other methods, and would then also lead to performance increases. All right, so let's look at some results. First, we can have a look at the three baselines here, where we see that the from scratch baseline gives the best performance with around 80%. And we also see that if we don't protect against catastrophic forgetting, there's really a remarkable drop in performance. Then looking at the 5 regularization-based methods, we see that the hypernetworks give the best mean final accuracy with around 72%. And if we look at the 2 weight importance method, we can really nicely observe this trade-off between plasticity and stability. So here, the low during accuracies or comparatively low during accuracies show that even though the networks that we use are in principle able to solve these tasks quite well, when you train on multiple tasks, the weights get more and more constrained such that the networks can't really solve these tasks anymore. Then for masking, we see that the during accuracies are quite good, but it seems there's too much interference between the different subnetworks such that the final accuracies, again, look pretty bad. And when we do the protection with synaptic intelligence, again, we see this trade-off between stability and plasticity. Then coarse sets give the best performance among all these methods, but as I mentioned before, it's not directly comparable to the other methods used here. Next, we looked into a variant of MNIST called stroke MNIST, where you turn this image classification task into a sequence classification task by translating these images into sequences of pen displacements that will then draw out these images. And to turn this into a continual learning setting, we make use of this split MNIST scenario, where we subdivide the 10 classes into 5 times 2 tasks. For example, we classify whether the input was a 0 or a 1 or 2 or 3 and so on and so forth. However, we realized that this task is actually quite easy to solve, and to make things a bit more interesting and also to get a handle on task difficulty, we turn to sequential MNIST or sequential S MNIST, where we're now not looking at digits or single digits anymore, but actually sequences of digits. And so here we have an example for the sequence length 3, which would give us 8 different possibilities for binary sequences. However, we wanted to have still a binary classification task. So what we did is to sort these possible sequences randomly sort them into 2 groups to recover a binary classification task. We again ran continual learning experiments on tasks of different difficulty levels, and what's displayed here is the mean final accuracy of different methods for these different difficulty levels, as given by the sequence length M here. And we see that the multitask baseline is actually able to perfectly solve all of these tasks irrespective of the difficulty, and it's also better than the from scratch baseline, which indicates that there is some transfer between the tasks. When we look at the weight importance methods, we see that they are clearly affected by the difficulty. So the continual learning is affected by the difficulty of the individual tasks, which is interesting because from scratch baseline here, we know that individual tasks can actually be solved quite well. But this drop in accuracy here again shows this or highlights the stability plasticity trade-off, which is dependent on the difficulty of individual tasks. The other regularization methods, hypernetworks and masking, don't show this dependence and highlight again this dependence of the weight importance methods. Then finally, we looked at a natural language processing task called part of speech tagging, where the task is given a sentence to give a grammatical annotation to all of the words in the sentence. So the annotations could, for example, be verbs or propositions or nouns and so on. And there's a data set called universal dependencies that gives such annotations for many different languages. And we turned this task into a continual learning task by sequentially training on 20 different languages. And to solve these tasks, we use bidirectional LSTMs and pre-trained word embeddings to map from the dictionary size into an embedding space. And when we look at the results here, we see quite similar trends as for the 2 experiments before, where again, hypernetworks give the best mean final accuracy within these regularization methods. Here, the difference to the weight importance methods is not as big, but we can again see this slight dependence on the stability plasticity trade-off. And yeah, also the other results are quite consistent. So to conclude this experimental results part, we adapted different data sets for sequential data for continual learning experiments. We established a fair comparison between a variety of different continual learning methods. And we showed that in many settings, weight importance methods can actually work well, which is a bit in contrast to how they're being portrayed in the literature. However, we also showed that there is this dependence on this task complexity, which is mitigated a bit by, or which is, so we see some performance differences when we use hypernetworks, which are not directly affected. And here I also want to mention again that all of these data sets, as well as the implementations, are freely available online. So if you want to compare to some of these methods or use some of these data sets, you can find the links in the archive paper. So to conclude the 3 parts that you hear today, in the first part, Maria told you about our analysis on why weight importance methods are kind of differently affected or are affected by recurrent processing, and that we concluded that working memory requirements really governing this affection of the weight importance methods. In the second part, Christian introduced hypernetworks as an approach to continual learning, which is not so susceptible to the problems of weight importance methods. And in the third part, I showed you that these theoretical differences actually also manifest themselves in differences in performance on different real-world data tasks. All right, so with that, I would like to thank our collaborators on these 2 papers, as well as you for listening, and we're happy to take your questions. And I'm quickly gonna use my headphones here, so there's no interference. All right, please.
Thank you so much, guys, for your very interesting and in-depth presentation, I would say, on continual learning for recurrent neural networks. I think that more work is needed like yours to explore how continual learning can be applied to these kind of sequence learning problems that are often ignored by the rest of the continual learning community. So it was really a pleasure to host you here today and listen to your advice, hints, and results of your work on this topic. So maybe I can start with a question just to break the ice. So about hypernetworks, maybe I missed this part, but essentially these hypernetworks are conditioned on the task label, right? And do you see a way of, let's say, overcoming the use of task labels? Can an hypernetwork work theoretically also when you don't have like a clear separation between tasks?
So, do you hear me?
Yes. Yeah.
Okay.
We can.
Yeah. So, if I understood your question correct, so you're not asking where we can do task inference to figure out what task to solve. You're asking if there's not really a discrete boundary between tasks, but more a continuous stream of data.
Yeah.
No. So that problem is not considered by us. That's why we had this extra introduction slide where we say what we consider as continual learning, where we need this discrete set of tasks. If you don't have the task boundaries, then you would need to use another method.
So you don't see a way of somehow expanding your proposed technique to address also?
It really depends. If you really go from discrete tasks to continuous changing data distribution, then it's anyway questionable what kind of continual learning scenario that is. So there could be different scenarios, right? One would be you have a fixed data distribution, but you just don't obtain IID samples from that. And that is a very interesting continual learning scenario. And I think therefore you need to explore different strategies than the ones that we have been using. Also, they could also employ hypernetworks, but not the same way we do it. Yeah. If you really have a changing data distribution that changes continuously, which is not like you have a discrete set of tasks, but one data distribution that just drifts in space, that is honestly it's difficult for me to imagine where this is practically relevant, and then you definitely have to find some kind of trade-off between forgetting and learning new stuff, because then these task distributions will be overlapping. So I don't have a very good answer to you, because our method is really just tailored to this scenario.
For example, one common, more and more common, I would say, scenario is the class incremental setting, where you have a just unique classification problem and you have more classes over time. And of course, in that case, the notion of a task is not really appropriate, because if you encounter like a bunch of new classes, then in this unique classification, probably you want also to classify any class with all the classes you encountered before. So you can separate, let's say, the outer space. So in that case, do you see a way of applying hypernetworks in that case, or is the same answer as before?
So this is still discrete in this case, and this is a scenario that we consider in our paper. So in some part of the literature, it has been termed CL3. So the one figure that I showed you, where we have to infer the task identity automatically, that essentially acts in this case, where you have where the other methods have, so where we have to learn a growing softmax. For example, you start with a 10-dimensional softmax, for next task it becomes 20-dimensional, and so on. So you really need, at the end, you want to have one single classifier that is able to, when it gets an input, to tell you from which task and from which class it is coming. In this case, that is what we have to do task inference. So we either need to figure out how to pick the right, or we do the approach that I presented on generative replay, where we have via the hypernetwork task-specific replay models, task-specific generative models, that allows us to do essentially pseudo-multitask learning. So I can replay data from all previous tasks, and I have the current data available, so I can train on all data at once. And this allows me to, of course, train a classifier over everything I've seen so far.
Thank you for your answers. And are there any more questions from the audience?
I have one. So, do you think that weight importance method can be adapted to recurrent neural networks, or do you think that there are no possibilities?
Okay. Can you hear me?
Yeah. Yes.
Yeah.
So I don't know exactly what you mean by adapted. If you're worried about performance, I said we were a bit surprised that in many of our results, actually they perform quite well, because from the literature we saw that many people have found results where they didn't perform quite so well. Whereas in our case, where we really granted a lot of hyperparameter search resources, we found that they actually in most cases perform so well. Of course, with the caveat that if you increase a lot working memory requirements and you have too many tasks, then there is a limitation that they reach. So I think in many cases, maybe they don't even need to be adapted and they perform quite well. Now, whether something could be done to overcome exactly this limitation, to be honest, I haven't really thought much about it. I don't know if you guys have any specific comment.
I would have a comment here. So this would relate to the intuition that there's these different subspaces in the hidden dimensionality, right? So this, of course, is a bit of a simplification, because in reality, these subspaces will never be completely orthogonal, and there might be some joint processing. And so we found a recent paper which actually makes use of this, kind of that there's joint processing between different tasks, and that really tries to optimize the way that these hidden subspaces in the hidden dimensionality are used efficiently, so reused by methods that require similar dynamics. So this was published in NeurIPS recently. So this I just thought this was an interesting kind of approach to really try to organize the hidden space efficiently, so to say. But nevertheless, there's still this clear limitation that you somehow have to work in the same hidden space always, whereas with the hypernetworks, you really circumvent that by kind of having a fresh space per task, where you can use the full capacity, which is really the big advantage of this approach.
If I may add additionally and refer to the supplementary of our paper, so there's nothing that prevents you to use these weight importance method in an unconventional way and also task condition them. So give the task condition as input in order to allow them to do task conditional processing, and that will make them perform much better. This is of course only possible if you have the task condition during inference time available, but if that's the case, you can make them work much better in this scenario.
Yeah, okay, thanks.
Because Antonio, you once told me that you were finding difficulties in trying to apply weight normalization methods, right, on classic sequence learning problems, right? We
tried a little bit, and I think on permuted MNIST they work quite well, because the input is already orthogonal, more or less. So that's kind of give it for free. But if you, for example, train on split MNIST, it's much more difficult instead to make weight importance method work. But I mean, this was just our experience. And also what you say about the hyperparameter selection is true, but it's quite problematic in a continual learning setting, because when you are writing the paper, of course you can do the hyperparameter selection, but when you are deploying the model, you can't do the hyperparameter selection because you don't have the future task. So.
Yeah, totally. Yeah, but I would say that this is a problem. This is also common outside the sequence learning problems, also in computer vision. I mean, not simpler, even simpler settings in continual learning. You know, almost every researcher and every paper out there is somehow leveraging the fact that we can fine-tune somehow these hyperparameters. But I agree with you, and I written in some of my papers, this fact that if you want an agent that is going to be deployed and has to learn continuously in the real world, of course, it has to possess somehow an approach that is robust enough to learn from any kind of data and without fine-tuning along the way these hyperparameters.
Yeah, exactly. It's not specific to recurrent models, but it's a general problem.
Do we have any more questions, comments for our guests? All right, so
I think there's a question in the chat, if I might just answer that.
I think I missed that, yeah.
So somebody wrote, can you re-explain what the stability plasticity dilemma is? So yeah, of course, it's just the fact that whenever you're learning many things in sequence, there exists this trade-off between having to remain stable, or your weights having to remain stable, such that you can still solve tasks that you learned before, but also some of them, at least, still remain in plastic in order to be able to learn future tasks. So it's only this, and of course, the more stable you are, the less plastic you are, and vice versa.
Thanks, guys, for your time and your very interesting insights that you gave us today. So I will send you an email to ask for your slides, if that's possible, so that we can upload it on our forum and people can discuss, continue the discussion there. So thank you all, actually, for joining us today. And I invite you to join as well for the next group session. Every Friday we have one at the same time. And I would say good evening and have a nice weekend.
Thanks a lot.
Yeah. Thanks a lot for the interview.
Bye.
Bye. Have a good weekend.